Hi, so what we're going to talk about now is how to actually use that limit definition of a derivative that was covered in the last video to find the equation of the tangent line. So finding the equation of the tangent line is a very important type of problem in calculus. You're going to do it a lot. Those tangent lines can tell us a lot of important information, and being able to find the equation of them is really important. So since the only way you know how to find a derivative right now is through that limit-taking process, we're going to do some practice problems, some examples, and show you how to use that derivative process to find the equation of the tangent line. So we're just going to jump right into the example problems. So the first thing we're going to do is find the equation of the line tangent to x equaling -2 to the function f of x equals x squared plus 3. So our final answer should be the equation of a line. So just real quick, before we jump into doing any calculus, we need to remember what the equation of a line is. So you probably work with y equals mx plus b, your slope-intercept form of a line. So we want our final answer to look something like that, which means that we need to know two pieces of information. The first thing we need to know is that m. We need to know the slope of the line at the point that we're interested at, that x equaling 2 point. And we also need to know the y-intercept. We need to know b, so your y-intercept. So we need to be able to find both of those things in order to write the answer to the problem. So we're going to keep that in mind. So in order to find slope, we need derivatives. So our slope, our m, is really just f prime of x. So what we're going to do now is we're going to use our limit process to find the derivative of x squared plus 3, and we're going to use that derivative function to find our m, our slope for this line. Okay, so let's just jump right in. So just like before, let's find the first part of our difference quotient before we plug into our limit. So we plug in that x plus delta x anywhere we see an x. So we get x plus delta x all squared plus 3, which is just x plus delta x times x plus delta x all plus 3. So we have to FOIL those two binomials together, and when we do that, what are we going to get? We're going to get x times x, so x squared, plus x times delta x, plus delta x times x. So we're going to get a total of plus 2 x delta x. And then we got to do our last for FOIL. So delta x times delta x, so plus delta x squared, and then tack on that plus 3. So now we're ready to plug into our derivative limit definition. So we have f prime of x equaling the limit as delta x approaches 0 of our difference quotient, which is f of x plus delta x. We can plug in this thing up here, x squared plus 2x delta x plus delta x squared, all plus 3, minus our f of x, remember to put it in your parentheses, x squared plus 3, all divided by delta x. Okay. So now we got to distribute that minus sign, that negative sign, and then we can simplify some terms in our numerator. So again, I'm going to make this a positive sign by distributing the negative to the x squared, cross out that plus 3 and make it a minus 3. So now we see I have this positive x squared here in the front. It's going to go away with this negative x squared. Positive 3, negative 3, they cancel out. Now let's just write what we have left in our numerator. So we're going to get the limit as delta x goes to 0 of 2x delta x plus delta x squared all over delta x. Okay, so just like the example in the last video, we're going to factor a delta x out of the top because we can't just cancel it as is right now. You can't cancel anything between the numerator of a fraction and the denominator unless you can factor it away. You can only cancel when it's between multiplication. So we're going to get delta x times 2x plus delta x all over delta x. So now just like before, cross out our delta x's. So now we can take our limit by plugging in 0. So when we plug in 0, we're going to get 2x plus 0, or just 2x. So our slope function, or our derivative, f prime of x, is just equal to the function 2x. So looking back at the original question, it asked us for the equation of the line tangent at x equaling -2. So that means we need to know the slope at x equaling -2. So why don't we plug in -2? So our slope is going to be f prime of -2, which is 2 times negative 2, plugging into our derivative. Then we have negative 4. So one of the uses for derivatives is to find the slope of the tangent line, which is why the derivative is so important for these types of problems. Okay, so now we know the slope of our line. So that was the first piece of information we needed to know. So let's mark that with a 1 to remember. Now let's find our y-intercept. So we know an x-coordinate on the curve. And since we know the x-coordinate, we can go back and find the y-coordinate of that point. So looking back at our original function, which was x squared plus 3, we need to find the rest of the coordinate point for x equaling negative 2. So let's plug in negative 2 for x and see what that is. So we get negative 2 squared plus 3, which is going to be 4 plus 3, or 7. So the point, negative 2, 7, is on this curve, this parabola, which means that since we're finding the line tangent at that point, the point's also going to lie in our line. So what we're going to do now is use that point to help us find that second piece of information, our y-intercept. So maybe you guys have seen this equation, this y minus y1 equals slope, or m, times x minus x1, your point slope formula of a line. This formula is really useful because it's really easy to just plug in all the pieces of information you have, simplify down to your slope-intercept form to get the equation of your line. So y1 and x1 are the y and x coordinates from a point on the line. Well, we know one of them, and we know m, so we can just plug in. So we're going to get y minus 7 equals, we found our slope to be negative 4 times x minus x1, so we have minus negative 2, so this is going to become a plus 2. And then all we have to do is simplify. So I get y minus 7 equals negative 4x minus 8. And now all we have to do is add 7 to each side to make it into that normal y equals mx plus b equation. So we're going to get y is negative 4x. Negative 8 plus 7 is just minus 1. So our tangent line at x equaling negative 2 has the equation y equals negative 4x minus 1. So that's how you go about finding the equation of a tangent line using your derivative. So let's do one more example then. Hopefully you guys will get the process down. Okay, so we're going to find the equation of the line tangent at the point 1, 1 to the function f of x equals 1 over x squared. So remember, we need to know our slope, and we need to know our y-intercept. So we need to find those two pieces of information. Okay, so we need to find our derivative first to find our slope. So let's find our f of x plus delta x so that we can get ready to plug into our difference quotient and take the limit. That's just going to be 1 over x plus delta x, the quantity squared, which is writing out it's just the binomials multiplied by each other. Put our 1 back up there in the numerator. And since we've done this foiling so often, I'm just going to jump straight to the answer. We're going to have x squared plus 2x delta x plus delta x squared there in the denominator. Okay, so now we're going to find our slope. So our slope, or our derivative, is going to be equal to the limit as delta x approaches 0 of f of x plus delta x, or 1 over x squared plus 2x delta x plus delta x squared minus 1 over x squared all over delta x. So again, we have complex fractions, so we need to multiply into the numerator and denominator of our big fraction by the denominators of our little fractions. So we're going to multiply in by x squared times x squared plus 2x delta x plus delta x squared over itself. So I'll just put those quotation marks there. We don't have to rewrite it. We know what it means. Okay, so let's do that. So when we distribute this term into the first fraction in our numerator, that big whole quadratic mess is going to cancel, and we're just going to be left with, let's see, write our limit down first. So that's going to cancel. We're going to be left with x squared minus, oh, forgot to put the parentheses in there. Those are important. X squared minus, and then when we distribute this into the second fraction, that x squared term is going to cancel. We're left with parentheses x squared plus 2x delta x plus delta x squared all over delta x times x squared times x squared plus 2x delta x plus delta x squared, all in the denominator. So now, just like we do in every single problem, we're going to distribute that negative sign and see what cancels. So make this a plus out here, distribute, we get a minus x squared, minus 2x delta x, and a minus x squared. Delta x squared, sorry, at the back. So we have a positive x squared and a negative x squared. Those two cancel. Let's write what we have left and see if we can take our limit now, cancel anything out. So we're going to get the limit as delta x goes to 0 of negative 2x delta x minus delta x squared all over delta x times x squared plus 2x delta x plus delta x squared. Okay, so just like we did in the last problem, we have a greatest common factor of delta x in the numerator, so we can factor that out so we can cancel it with the denominator. So we're going to have delta x times negative 2x minus delta x all over that nasty long denominator of delta x times x squared times the quantity x squared plus 2x delta x plus delta x squared. Okay, so now that we factored out that delta x, we can cancel the one in the numerator with the one in the denominator. We can plug in for 0 for delta x and see what happens. So we're going to get negative 2x minus 0 over, we get x squared times x squared plus 0 squared, which is just going to be negative 2x over x squared times x squared, which is just x to the 4th. But now we have an x in the top, 4x's in the bottom. We can actually cancel some stuff out here and simplify. So cross out that x, cross out this exponent, make it a 3. So our final derivative here, our slope, or our f prime of x, is just going to be negative 2 over x cubed. Which means we were interested at the point 1, 1. So our slope here is just going to be the derivative evaluated at 1. So we get negative 2 over 1 cubed, which is negative 2 over 1, or negative 2. Okay, so now all we have to do, that was our slope, so piece of information 1. All we have to do is plug into that point slope formula that we had, that y minus y1 equals slope times x minus x1. Simplify, and we'll have the equation of our tangent line. We'll be all done. Okay, so let's plug in. So we knew that our point was the point 1, 1, so we'll rewrite that there for reference. So we get y minus 1 equals our slope of negative 2 times x minus 1. Distribute this negative 2 through first. So we're going to get y minus 1 equals negative 2 times x, so negative 2x. Then we have negative 2 times negative 1, so we're going to get plus 2. Add 1 to both sides to simplify, make it our y equals mx plus b equation. So we get y is equal to negative 2x plus 3. So that is the equation of your tangent line at the point 1, 1. Okay, so that's everything I have for you today. I hope this helped figure out the process of using that limit definition of a derivative to find the equation of a tangent line. Hope this helps with your homework and your classwork, anything like that. Have a great rest of your day.